So we get started here. Raise AST 111. So I'm going to be recording this video of, like, say, the my responses rather to your questions for the questions about space form that we did, or the class did, about going on, I say again, 2 or 3 weeks ago. And incidentally, let me go ahead and sit down here. I'm gonna have to stand up periodically because I'm inside this classroom, and if I don't stand up or move around, the lights will go off. Okay, so but everyone, just wanted to say this before I get started with responding to your questions. First of all, the point of this voice thread is to create an ongoing dialogue between myself and all of you about these various saying again things that we're wondering about in the field of astronomy, as well as though some questions you actually gave to me also pertain to space exploration. So this first question, as a matter of fact, also gets into space exploration or space colonization. Okay, but still, quite a few questions that you posed were about black holes. And the week after this video was recorded, this class covered black holes and general relativity. So many of those questions are probably have been answered by the material that you actually covered in that week. However, I'll still address those questions. I will also say that several of these questions that you posed show me that there's a couple of concepts that we've already covered in this class that several of you are not quite grasping or quite understand. So therefore, I will definitely spend some time answering those questions to help make sure that you understand those concepts and principles. I also want to say that a few questions are also quite vague, and I had a hard time trying to understand exactly what you meant with some of your questions. But I'll still address those um, as well as any others. So let's go ahead and get started with these questions. So the first question says, if humanity were to reach Mars and attempt to create a settlement, roughly how long will it take until such a settlement will be able to flourish on its own? And it also says, how much could humanity actually do to make Mars a more suitable living environment? So I have several of these that I've had some responses written out for them and things like that. So you might see me glance down a little bit, just make sure that I mention everything that I already have written down or already typed up, okay? Or have, like, just say again, consulted other sources about this, just in case that I'm mistaken about anything. And everybody, it's okay to say again to go back to say again sources. All or say again we respond to somebody. Okay, keep that in mind. Say that's you don't necessarily remember everything. Okay, it's always good to consult sources. But still, here's the thing that I want. Here's my response to this first question. And the way this voice thread is going to work is that you can look through the voice thread to find the questions that you actually pose and look at those answers. And you can say again, and also, but it's good to look at the entire thing. And I'm going to tell you this now because you asked so many questions. This is going to be a quite long presentation, so you're going to watch this in steps. Okay. But anyway, get back to this question. Say how long would it take for that let's say again that settlement to flourish on its own? It will take easily decades to maybe centuries. And you got to think about how long it took mankind to actually basically have established civilization on this planet, and this is the one planet in the solar system that's made perfectly for us. Okay, so Mars, on the other hand, which is our best choice for a Plan B, and that's by the way, it's going to be pertaining to a question that somebody else posed later on. But as far as, like, a planet perfectly suited for human beings as we are, of course, Earth was perfectly designed for human beings. Still, Mars, with its lower gravity, its lack of atmosphere, and like I said, lack of vegetation and things of that nature, what happens to everyone is that to be able to like be able to get to Mars, first of all, that in itself is going to be a challenge. But if we understand once we get on Mars and like start colonizing Mars, it will take, like, say, decades, maybe even centuries, because what happens is everything that human beings do will have to change. They'll say again the way we the way we bathe, the way we cook our food, the way we have to grow our crops, just walking. All these different things will have to change because again that lower amount of gravity on Mars. Not to mention the fact that with lack of an atmosphere and a magnetic field, we have to actually have to adjust to like how we're going to take radiation. We don't have that protection on Mars like we do on Earth. Rather, we will not have that protection on Mars as we do on Earth. Okay, Mars is colder, a lot colder than Earth. So therefore, what happens is we have to adjust for that as well. So I'm getting to like the second part of the question: what we need to do to make Mars more suitable? We have to terraform Mars. Terraform literally means we got to change that planet to be more like Earth. One particular thing that we talked about is Mars does not have a greenhouse effect. That's the greenhouse effect of Earth allows Earth to be relatively, say again, warm, and therefore warm enough or the right, say, temperatures for human beings. Okay. The problem is with our planet currently is that with climate change, the greenhouse effect is intensifying, and that's making the planet hotter than it should be. And that's the problems we got right now. But still, everyone, what happens is that if we want to, so again, make Mars more suitable for us, we got to terraform it. And terraforming could take decades. Okay? Looking down here, my notes here, just read this off. It says terraforming Mars will make it more suitable for humans is even a longer term goal and will involve altering the atmosphere, increasing temperatures, and possibly introducing biological systems to create a habitable environment. One of the things we thought about doing is dropping a lot of dark material around Mars and therefore make the planet more absorbent. Well, I mean absorbive to sunlight. So the more sunlight it can absorb, what can happen is it can raise the temperature of the planet and melt some of those ice caps around Mars that are full of carbon dioxide. And so what happens is if we get more carbon dioxide in the atmosphere, that would make the atmosphere that would actually increase the greenhouse effect, and that would actually allow heat to be trapped on Mars, and therefore by having more heat trapped on that planet, it makes the planet warmer, and therefore raises the overall temperature up, so that we can actually potentially go around Mars and grow crops, for example, or maybe like say again, actually start establishing like vegetation. We can grow trees, and that allow us to breathe without use of a special spacesuit. Also, without the lack of atmospheric pressure, that's a problem as well. So what happens is that if we increase the atmosphere on Mars and therefore increase the atmospheric pressure of that planet, they can actually allow us to be able to walk around, and we don't need a protective spacesuit. Because on Mars, you will need a protective spacesuit in order to, say again, survive. Okay? So again, long story short, I already told you a long story already. And there's whole books written on the subject. There's whole books written on this particular question alone, or these questions alone. So again, it will take a long time for it to flourish on its own because in order to sustain that let's say again that settlement or that colony, you had to have agriculture. That's what's actually kept civilization on Earth going for so long. The fact that we can grow crops and do these other things as well. Domesticating animals is another part of that. Which again, we're gonna have to find a way to get animals on Mars too, or maybe everybody just become vegetarian, or vegan, whatever. Maybe that's how we're gonna make it. And I'm pretty sure those of you who are already vegans or vegetarians, I'm pretty sure you can appreciate that. Okay, so I spent a long time on that first question. So let me not spend a lot of time on this one. Okay, what's the true scale of the universe? Again, as far as we can tell, the universe is probably infinite. Okay, so if it's possible it's infinite, yes, it's a possibility it's infinite. That means that all the matter and energy that is in existence, which is the universe itself, the universe is the sum of all matter and energy. Okay, so if it indeed is infinite, everyone, as we like to think it is, there it is. But then how would that change our understanding? If it's like, let's say for example, if it's finite, if it was finite, that would actually affect, saying again, the existing cosmological models And cosmology, which this class will be learning about, cosmology, everyone, is truly the study of the evolution, or I should say formation, evolution of the universe. Okay? So if the universe is truly infinite, everyone, that's not necessarily going to affect certain models, but models that actually say that the universe is indeed finite, there's going to be an end to it, those will be affected. Okay? So, but still, actually learning that this universe is truly infinite, that would definitely affect certain, like saying again, certain ideas that we have. Now, back to the scale itself, we do have an idea, or rather, we can calculate what's the scale of what we call the observable universe. That's the amount of universe that we can directly observe. And the observable universe, everybody, the size of that, or the scale of it, is based on the speed of light and the age of the universe. As far as we can determine, based on the best measurements and observations we have made, observations made by space telescopes, ground-based telescopes, data that we collected, models that we have made, calculations we have done, the universe is about 13.7 billion years, or maybe close to 14 billion years old. So you take that age of the universe, multiply that by the speed of light. The speed of light is 300,000 kilometers per second, approximately. Multiply those two numbers together, and that'll give you the size of the universe. So again, if I write this on the board, the observable universe, let's say the radius of it, the radius of the observable universe is equal to the speed of light in vacuum multiplied by the age of the universe. And again, you'll see this fact again in a later video in this class. Okay, but that's the amount of the universe that we can potentially observe. That's still not the whole universe. Okay, because one thing that stays in this universe we cannot directly observe using light waves, and you can be learning about that as well. It's called dark matter. So what happens to everyone is that and dark, and that's also dark energy. So between the two of those, everyone, dark energy and dark matter, which cannot be directly observed, if that stuff indeed is out there, and if indeed it makes up the majority of the universe, we cannot see the entire universe using light waves. We're gonna have to use something else to observe, let's say again, the universe. And of course, we're working on that. In this previous chapter we just covered, chapter 14, you read about gravitational waves. Gravitational waves are, for example, something else that we can use to probe deeper into the universe. Okay? So again, it's true scale of it, we don't know yet. And also, everybody, if the universe indeed has a limit, that can affect, I say again, a lot of theories about the expansion of the universe and what's going to happen as it continues to expand out. So, very good question. A lot of stuff discussed there. So, next one: do black holes actually regularly absorb planets and stars, or they're too far away for such objects to do so? And the answer to everybody is this one is black holes do not regularly absorb, don't typically absorb matter. They don't go around sucking things up. Okay, they're not vacuum cleaners. Saying black holes just don't go around sucking up things. Okay, let me put this. Let me read this off. Black holes typically absorb matter when objects stray too close to their event horizon. So again, everybody, what happens is if you get too close to a black hole, yes, it will pull you in and you can't get out. Planets and stars get a little too close to black holes. Yes, what's going to happen is they're going to end up going to like an orbital decay and get eventually spiral in. Well, some of that matter will spiral in. Other pieces of matter might be shot out. Okay. To save time with this video, I won't go in more details about why things might get shot out of the black hole, but I invite anybody whoever asked this question, which I know who asked the question, but the person who posed this question, I invite you to actually continue on that discussion with me in your comment on this voice thread. Okay. But what happens is, if you're so far away from the black hole, or you beyond the black hole's event horizon, no, it's not going to actually pull you in. But once you're within the black hole's event horizon, yes, the potential of you being pulled in it goes, of course, through the roof. It's more likely it's going to happen. Okay. When I say you, I'm talking about like you, your planet. What I mean by you, I mean your planet or your star. They get a little too close. Yeah, they're getting absorbed in, or rather, they're going to be gravitationally attracted and pulled in to the black hole. Okay, but they don't go around sucking up stuff. So they regular soil bounder? The answer is no. But that being said, it also depends which black hole you're talking about. The supermassive black holes, they're the center of galaxies. Yeah, they're constantly probably accreting matter around themselves. And more about those later. So next question: how far has human technology traveled from Earth? And how much of our universe or even our galaxy have we actually seen? So how much by let's say how far has human technology traveled from Earth? Pretty much the furthest object we have sent is Voyager 2, and Voyager 2 got out of the solar system got about approximately about over 10 years ago now. It just reached the edge of our solar system, and now it's got out of our solar system, and it's now what we call interstellar space. That's the space in between stars. Okay, so the farthest traveled one is now Voyager 2. We also have New Horizons that's exploring the outer parts of our solar system, but again, Voyager 2 has actually literally left the solar system. Okay, so now how much of the universe have we seen? That goes back to the observable universe question. Okay, how much of our galaxy have we seen? We've seen quite a bit, but we have not actually seen the entire galaxy because, of course, we're actually inside the galaxy. So therefore, how much have we seen? It goes down to the data we've collected from, let's say, our space-bound telescopes, our Earth-bound telescopes, and of course, anything that's been observed by our most distant exploring spacecraft. Okay, excuse me, spacecraft. Let me get some water real quick. So again, very loaded question, but that's pretty much the answer to your question. And everyone, I'm not going to again quote any like exact numbers because what happens is those kind of facts will change. How much of our universe we observe that is changing daily. Okay, how much of our galaxy have we observed? Just the galaxy, just our galaxy, we've observed quite a bit. Okay, we've discovered many stars within our galaxy, star clusters within our galaxy, that and so on and so forth. So if you really want to get an idea about how much we actually directly observe, this is where the lab comes in. If you look at the stuff that we have done in lab and all the different things that you can actually observe as far as like the information that you can we can ascertain from using the software that we use in lab, that will give you a good idea about how much we've actually seen. Okay, but this right here, this equation, back to this equation again, this tells you basically how far out we can see potentially by using light waves. How far out can we see? Is this. That's again the observable universe. Okay? So again, if you got more questions about that or you want clarification on this particular question, again, let me know. All right? This is one of those vague ones. Okay, about how is space operated and how was it created. Okay? So when you ask about how space is operated, I'm not quite sure what you mean by that. Okay. Now, here's one thing I collected from a source. It says space operation refers to international collaboration, exploration, and adherence to what they call the Outer Space Treaty. If you mean by that, okay, like how is it operated? Well, the exploration of space is done again by collaborative effort, and the way that and it has to be done by collaborative effort. If we're ever going to actually explore space or colonize another planet or anything like that, we got to collaborate. Human beings have to work together. All these different things, if I want to use that word for it, all these little silly differences between ourselves, if we ever going to actually again explore space like we want to, we got to collaborate. We got to get past again these differences between ourselves. And some people have made the argument to me that we'll never colonize another planet because we won't actually get along enough to do it. Okay. Some will argue that saying again God won't allow us to do it. Some people made that argument to me. Okay. So, but again, how was it created? Well, most astronomers will say, if you talk about space, it's in like the universe itself. They will say it's something that's related to. Somebody might say it's related to the Big Bang, like how the universe got created, and the answer is no. Everybody remember this right now. I'm gonna say this again. You'll hear me say this again in a later video in the class. The Big Bang Theory does not explain how the universe began. Okay? It does not. Okay, the Big Bang Theory explains why the universe is expanding. Like from a physical point of view, what probably caused the expansion of the universe, or what got the universe to the state it is now. That's what the Big Bang Theory looks into. It's not about how the universe was created, because the universe existed before if this event indeed happened, before the Big Bang indeed happened. If it indeed happened, the universe, the matter that makes up everything that the universe is today, that matter already existed. At that point in time is where physics, as we know it, breaks down. Okay, physics beyond, like say again, beyond, like say you talk about beyond the Big Bang or before the Big Bang, physics as we know it breaks down, and we don't understand what happened. Okay, so and some people, like say again, who love to like talk about what scientists don't know. Of course, like to step into like, aha, you see, aha, I got you. So saying it's God, saying, so aha, I got you. No, don't be doing that either. Okay, because again, what happens is, first of all, you need to understand. Like I say, I'm not saying you need to agree with these people. I'm saying that what you need to understand is why they're saying these things. Okay, it's when understanding comes, like say, with understanding everyone, we can actually come to one accord and actually come to, like say again, a better understanding. Okay, so again, how was, like saying, space itself created? Well, like I say again, long story short, space is we set talk about like the universe expansion. That was what the Big Bang is trying to explain. Why is the universe is expanding? Okay, but beyond that and how it's created, that's something else. And do people have ideas about this? Of course. Okay, the science of it. Now, of course, we're talking about, like say again, the spiritual side of things. Well, of course, everybody says we already got that answer. Okay, and some say that answer's not good either. So that's a quite loaded question. Okay. Again, if you want more clarification, um, put that in your comment. Okay. How long do the stars stay in space? Again, very vague question. Okay. How long do stars stay in space? So this can be interpreted two ways. If you're asking like how long do they stay in place, like in the positions they're in, the answer is stars actually move. Okay. The reason why they don't appear to be moving is because they're so far away from us. The stars you're looking at, the sky, the stars you can see tonight. I'm not talking about the sun now. Look more about that one later. But I'm talking about like the actual stars outside our solar system. Those stars actually move. If you actually look at that star or that position in space that star is in long enough, you actually see that star shift its position. Okay? So, and also stars, of course, saying night in, night out, they do appear to be shifting because of the motion of the earth. Okay? But I'm talking about the actual, like say, the stars themselves. No, the stars actually don't stand still. They're actually moving. They actually move within their own star systems, and they rotate. So stars don't actually stand still. Okay, so that's the answer to that more or less. But you ask like how long do they like stay in space? In other words, how long do stars live? Well, that depends. Stars can live for either like hundreds of millions of years or billions of years before they go to their next phase of their lives, and they become something they're not stars. Okay, so again, like I said, whoever posed that question, again, just put in your comment what exactly do you mean by how long did they stay in space? Are you talking about like them staying in their positions? And the answer is no, they actually do move. But again, the motion is going to be very gradual from our vantage point on Earth because we're so far away from them. If you're asking how long did they live, well, they live very, very long time, millions to billions of years, in just main sequence alone. Again, when I talk about millions and billions of years, I'm talking about how long they stay in what we call main sequence. Okay, so again, clarification is needed. All right, how long did the moon stay in one spot, and why did they move so slowly? This goes back to again with the what I said about stars. Moons do not stay in one spot. Nothing in space stands still. Everyone, nothing in space stands still. Nothing. Okay? Everything in space is moving relative to something else. Okay? Why did they say now if it seems like the moon's taking a long time to move, again, it's because you're actually so far away from it. Okay, our moon actually travels around our planet quite fast. It's traveling through space actually quite fast. But the only reason why it may not look it's moving so fast is because it's actually so far away. The distant moons around other planets, again, why they look like they're moving very slowly is because again they're so far away. So they're actually moving quite fast. But because we're so far away from them, that's why they move. They look so like they move so slow. I give you say again a point here about this, or another point about this. Okay, let's say again let's say you go out to this let's say you go out to like say again to the ocean, go to the beach. Okay, and you look at say again you look at a ship that's still like in sight. Okay, if you look at that ship out there like across the ocean, if you can still see that ship, let's say like you see the top of the ship, the mast and all that stuff. Let's say again, if it's a sailing ship or if it's a cruise ship, you can see basically the whole ship. Let's say you can still see it. What happens to everybody is like, let's say you take a look at that ship and then you look at somebody like on the beach with you. That person who's moving on the beach, it's going to appear like they're moving back and forth faster and they're moving back and forth in front of you. It's going to appear like they're moving faster than that ship that's across the water. Okay? And that ship across the water is actually probably moving quite fast. But because it's so far away, it don't seem like it's moving as fast as this person moving right in front of you. And moons are like that on around distant planets. They're much farther away than that ship is. So if you look through your telescope at that, let's say again that moon, why does it look like that moon moving so slowly? Because again, that moon is so far away from you. That's why it appears to be moving so slowly. In actuality, it's flying probably through space as fast as a bullet. But the thing is, because again, it's so far away from you, you can't tell. Okay. Again, those who are in lab, you're actually you know this. We can take the software we use in lab and time lapse things such that we actually can see potentially how fast these things really are moving. And by the way, I'm talking about when they're moving. I'm talking about their orbits in space. Moons rotate too, just like stars. Stars and moons, they and planets, they all rotate. Okay. Again, nothing in space stands still. Right? Would our galaxy be absorbed into a black hole? Okay. The answer is no. Right? We're not going to be absorbed by a black hole. There's a supermassive black hole in the center of our galaxy. It's not absorbing the whole galaxy. It's not happening. Okay. Do you have some matter that falls within into the supermassive black hole? Yeah. If you get too little close to it, yes, you do have some matter that might fall into that black hole, but our galaxy will not be absorbed into that black hole. However, everybody, what will happen is, say again, if things are playing out the way we see them, what's going to happen to our galaxy is that our galaxy is going to eventually collide with another galaxy, and that galaxy is going to be Andromeda. So the Andromeda galaxy and the Milky Way galaxy are coming towards each other, and they will eventually will collide. But it's going to happen, everybody, over the course of the next billion years. Over the next 4.5 billion years, according to one source, and again, you can look this up again later. But over the course of the next billions of years, our Milky Way galaxy rather is going to collide with the Andromeda galaxy, and they're going to merge into one. Okay, so we're not worried about any black holes sucking us up or absorbing us. What we're worried about is, let's say again, our galaxy colliding with another one. Which again, like over the next billions of years, I'm not gonna talk about you guys, but I know I'm gonna be gone before any of that happens. So, though I'm not worried about it. Okay. How many light years is Earth from the sun? The answer is much less than one. Our planet is not light years away from the sun. Our planet is what we call light minutes away from the sun. So a light year, everybody, is the distance that light will travel in a calendar year. Okay, so if you take 365 days, convert that 365 days into seconds. Convert that time into seconds. Okay, and if you to take that time and multiply it by the speed of light, that'll tell you how far light travels in a year. Okay. Now, let's say you do the same calculation, but now you take about this. Okay, How far is Earth from the sun? All right. It takes roughly 8 minutes, a little bit over 8 minutes, from Earth, from the sun rather, to get from the sun to Earth. So it's going to take about 8 minutes. Okay. That 8 minutes, everybody, represents how far the two of them are. So therefore, if you say like, okay, how far does light travel in a minute? And let's say you calculate how far light travels in a minute. Based on that calculation, Earth is 8 light minutes away from the sun. So the Earth is not light years away from the sun; it's light minutes away from the sun. Okay, so that's the answer to that. So it's not a full light year; it's only 8 light minutes. All right. Next question is, which star is most common in the universe? The answer, everybody, is, I'm gonna put it on the board, is a red dwarf. The most common type of star there is in the universe that we know of is the red dwarf. Okay, red dwarf stars. Now, again, a red dwarf, everybody, is not like a white dwarf in the sense that it's not a collapsed star. A white dwarf is a star that's died and collapsed. Okay, that's what's left over from it. A red dwarf, everybody, is a main sequence star. And remember, what determines the lifetime of a star, everyone, is its mass. The more mass a star has, the shorter it lives. Red dwarfs don't have a lot of mass. A red dwarf is smaller than the sun is in terms of mass. So therefore, because these stars have very low mass, they live long. And so therefore, most of the stars out there, the most common ones are going to be these because they live so long. Okay, one source says about 70 to 80% of the stars that are basically known about are red dwarfs. Okay, but again, even I say again, but don't quote that number. Don't put that number like in your mind. Say like, okay, that's what it's got to be. Here's the thing you need to remember: the most common star there is a red dwarf. Okay, and again, the reason why it's so common is because they have very low mass for a star, and because since they have such low mass, that means they can live for a very long time. Okay, so again, all the stars that got a lot more mass than them, they're pretty much like burning out, extinguishing, saying again, at a faster rate than the red dwarfs are. Okay, so somebody might be say comment on that, say like that's why certain people, the population is probably on Earth, for example, maybe why the population on Earth is like, so many like people like this, for example, like so many like people within this certain demographic. It's because those people also the ones that live the longest, perhaps. Okay, but actually, people are human population is much more saying again a different beast altogether as far as like problems you're trying to figure out what's going on with that situation. What happens to everyone is that again with stars, the most common star again is going to be the red dwarf. Okay, and by the way, if y'all cannot read that on the board, the word again I'm saying is red dwarf. All right, can the Earth survive without the moon? Yes, Earth can survive without the moon. Human beings, another story. So our planet can survive without the moon. Okay, this is what will happen without the moon. All right, this your world. Okay, stop being silly for everybody. So this actually is not our planet. This is actually a model of what we call the night sky. This is a celestial sphere. For those who didn't take lab this semester, you haven't seen this globe that much yet. But or you haven't been to the classroom with me and seen this globe in person. But still, everybody, what happens is, let's just imagine just for a moment, this globe represents our planet. What happens, everybody, that this globe is at a tilt because that represents the axis tilt of our planet. Remember, our planet, as it rotates on its axis, is tilted. And so, and more about that later with the question about the North Star. But again, everybody, what happens is because our planet is at this axis tilt, it has to be maintained, and it's being maintained by the interaction between the Earth and the Moon, the gravitational interaction. So everybody, what happens is that we were able to maintain, or our planet rather is able to maintain its axis tilt because of the moon. So what happens is if the moon all of a sudden was gone, Earth cannot maintain the axis tilt. And if Earth can't maintain its axis tilt, what's going to be affected? Seasons. And so what happens is without axis tilt, or without axis tilt, Earth will have no seasons. And without seasons, everyone, or what happens is agriculture is going to be affected. So without agriculture, if I said we have no way of growing crops or maintaining our animals and things like that, we are going to eventually die. Okay? There's some other things can happen too, but I'm just going to focus on just that aspect of it. But pretty much everybody, Earth can survive without the moon, but human beings and life on this planet, most of the life on this planet, that's not going to make it. Okay, that'll be the end. That probably pretty much be like the end of life on this planet. There's a channel. That's a a program rather on the History Channel called The Universe. In one episode of that program, they dedicated an entire episode to like what would happen to the Earth if we had no moon, or we all of a sudden lost the moon. It was a very grim episode, and they had several of them like that. But it was a very grim episode. But long story short, without the moon, if the moon was gone, that'd be the end of life as on our planet, especially human life. Okay, the Earth itself, the planet will survive, but I say again, but the moon itself, excuse me, but human beings on this planet, no. Okay. Again, seasons will be affected because, and that will actually that'd be the worst climate change you can think of at that moment. Okay, that's not the worst type of climate change, but like I said, without the moon, that'd be climate change problems through exponentially worse than what we got now. It will lead to the death of everybody. Okay. So next one, how will our lives be impacted if there were no stars? Well, since human beings are made of the same material that is actually processed and or exist in stars, what happens is without stars, everyone, as far as astronomy can tell, without stars, human life as we know it would not be like it is now. Okay, if there were no stars, life as we know it would be very different. We'd be very different beings if there were no stars. So I'm not saying that there would be no human beings, but human beings as we know it, they would not exist in this form. We would not be in the form we are now without the stars. Okay, we probably made of different materials. We probably look different. I know we look different, and we definitely gonna be made of something different if there were no stars. So life as we know it will be much different without them. Okay. So, and also, if stars all of a sudden were gone, let's say that if we lost the sun, forget about how bad it is to lose the moon. If we lost the sun, it's definitely a wrap for human life. That's it's a wrap. I mean, if we had no stars. Okay, I'm talking about like where we are now. If we had no stars, definitely that'd be a problem. And I'm talking about again, if that includes if those stars, talking about no stars, including like the sun being gone. Well, for one thing, the solar system itself will be thrown completely out of whack without the sun. The gravitational influence of the sun alone, if the sun was all of a sudden gone, the solar system will literally fall apart. Okay, so I don't want to spend too much time on that because it's too grim. Okay, is it possible for the sun to become a black hole? Again, it's one of those many black hole questions. The answer is no. It's not possible for the sun to become a black hole, everyone, because it's not massive enough. And this is something that you have definitely learned or should have like learned in chapter 14. Okay, the sun does not have enough mass to become a black hole. The sun can become a white dwarf, and we're saying that it will over the course of like billions of years from now. But the sun does not have enough mass to become a black hole. And everybody, the reason why mass is so important is because when a star dies and collapses, it's going to have a certain amount of mass to force particles together. The sun has enough mass and therefore has enough gravitational influence when it collapses that it can force, say again, particles into a particular state and become a white dwarf. Okay, but there's a force there that's keeping the material that makes up a white dwarf. There's a force. There's forces there. It's keeping that material from collapsing down further. Okay. In other words, it doesn't have enough mass and therefore have enough gravitational. Let's say again. Let me say gravitation. Let me just say gravitation. It don't have enough self gravitation to overcome that force that's keeping those particles from combining to form heavier particles. Okay. What makes up the white dwarf, everybody, is mainly things like electrons and stuff like that. It's like electronic material. So say again, there's not enough self gravitation to overcome that force to keep those electrons and protons and form neutrons. Okay, so if the sun had more mass to overcome that, it could combine electrons and protons to become neutrons, and therefore it become a neutron star. And if it had even further mass than that, its self gravitation can overcome what's forcing the neutrons to stay neutrons. It overcome that and have the neutrons combine to form something that's going to eventually lead to what we call a black hole. So the sun does not have enough mass to do that. Okay, and hopefully that's clear. Definitely ask me for clarification on that one. That's a good question. Right? Are there humans or beings similar to us in any other galaxies? And I'm gonna be quick with this one. We don't know. We do not know. Okay, we don't know yet. Is it possible? I'll argue that I don't see how you can argue against that. Okay, and I'm not just speaking on scientific grounds either. Okay, I'm not just speaking just on scientific grounds here. I don't see how it's possible to rule out the possibility of human beings being or any beings like us in depth other galaxies. Other star systems within our galaxy, even that. I don't there's too much out there. Okay? There's just too much out there. And I'm also saying that for another reason, but I'm gonna save that reason for anybody who wants to ask me what that reason is. Okay? So do we know? So the answer is we just don't know, but I don't think you rule out the possibility either. What's in black holes? The same thing that's in any collapsed star. Okay? So what's in black holes, everybody? Whatever is in a star when it collapses, that's what's going to be in a black hole. Okay? Is there a trace amount of dark matter there too? Maybe. Maybe. I don't know. But stars and dark matter are separate things. Okay? So I will say this: the answer to that question is what's inside of black holes. So what happens is again is it's going to be whatever's inside the stars. That being said, though, once something becomes a black hole, it's not that material is no longer chemical elements. Okay, whatever that material that makes up the black hole at that point, it could those neutrons, the stuff I was talking about earlier, it combines into some other kind of matter. So exactly what that matter is before it became saying I'm basically saying what it was before it became a black hole is whatever makes up the star. But once what makes up a star that has died, that is. But once it becomes a black hole, what that material is, we don't know yet. Yeah, we don't know. Okay. So again, but that one thing we can say about it is that material has collapsed down, and like I say again, and gravity has completely won the battle at that point. Gravity completely has won over the forces that's stopping that matter from collapsing down further to combine. Okay, and that force, by the way, those forces, everybody, it's called degeneracy pressure. Is the name of those forces. But still, what happens is gravity wins that. When gravity finally wins the war, it makes that material into something else. So it's a good question, exactly what it is. But I know what it used to be, and what it was again the material that made up a star that has collapsed at that point. That's or any star that's any heavy massive star that has collapsed down. That's what actually made up the black hole. But once it is a black hole, yeah, that's something else. Okay, take a little pause here, everyone. Let me get a drink real quick as you look at that question here. right? So, wonder how do they work? Again, a loaded question. How does black holes work? Again, what do you mean by how do they work? You mean how do they form? I've already talked about that earlier about how they form. Um, Again, when a big star runs out of its nuclear fuel, what I mean by big star, I'm talking about mass was and size too, but mainly mass. I'm referring to here. What happens to everyone is that when a star no longer can actually sustain a nuclear fusion reaction, that is the material that makes up the star, it's so stable at that point it can't fuse into anything. There's nothing else it can fuse into. When you have a massive star, start becoming have a core of iron. We reach iron. Iron is the most stable element there is. Okay, so but what happens there was that at that point, I say again, you can't. The star is made of stuff that cannot not fuse iron into something heavier. It don't have enough mass. It don't have enough energy to do that. To go beyond that. So the star basically collapses, and when it collapses down, it gets so hot that it explodes. And that's what we call a supernova. This is a massive star now. Not a star the size of we're talking about stars more massive than the sun. With this at this point. So, and by the way, everybody, there's a limit to like how massive an object can be before it potentially becomes a neutron star or a black hole. It has to be 1.44 times the mass of the sun. That's what we call the Chandrasekhar limit. Okay, so but still, what happens is once a star goes supernova, boom, it blows up. Boom. It's a big boom. Matter of fact, that's the background picture that I have for this presentation. Is basically a artist illustration of, let's say again, I use AI to generate it, but like I say again, it's a illustration of a supernova. Okay, big star went boom. So this big star went boom. It blows up, boom, and these outer layers expand out. Expand out. That material that expands out, that expanded material, it goes out into space. It becomes part of another star system. So another star is able to be born, or other stars are able to be eventually born because the material being blown away during a supernova event. But the remnant that's left behind, that remnant, what happens is it has no nuclear fusion, so therefore it has no outward pressure to keep gravity from making it collapse. So it keeps collapsing down and down and down. And because it got so much mass, that self gravitation can overcome the pressure on the inside that's keeping it from collapsing down further. Okay? This pressure again is not due to nuclear fusion. This pressure is due to the fact that electrons don't like to be next to each other, or protons don't like to be next to each other. They don't like to be next to each other like that. There's a natural force between them that causes them to be apart. Okay, and I'm of course referring to electrical repulsion. Electrons repel other electrons. Protons repel other protons. But let's say you got your electrons and protons, they combining together to form neutrons because gravity can overcome that. Gravity can also overcome the fact that they don't want to be in the same state together. It overcomes that too. So gravity is like saying again that self gravitation of the body. It collapses those particles down, and eventually they get to a point where you have all this mass. You have something greater than the mass of the sun. You know, maybe like twice or three times, or even greater than that, the greater mass in the sun. But yet it well, I want to say, and yet it has a volume smaller than this cap in my hand. Imagine something more massive, like several times the mass of the sun, but yet can fit in something not even this big. It can fit in something like smaller than this. This is the cap of one of my dry erase markers, or it can fit into a volume, everyone smaller than this light bulb right here. Could you imagine somebody trying to get something three times the mass of the sun, for example? Because I'm saying three because that's usually how much mass it requires to get to a black hole. But three times the mass of the sun, but something smaller than the volume of this light bulb. Because again, that's why the gravity of a black hole is so strong. Everyone, that's why. And it actually collapses down in like in this, and that's I'm talking about like the whole body of it. You know, when you get inside, that's one point where all the masses collapse down to a point where the volume is pretty much zero. And when the volume is like we have all that mass, but you have a volume of zero, we like to call that a singularity. And at that point, the curvature of space time is infinite. So at the singularity point, the curvature of space time, that's what gravity is, the curvature of space time. The curvature of space time becomes infinite. In other words, it's like a bottomless pit of gravity. So if I would draw a picture on the board like that, what happens to everyone is that this pit has a bottom. But with a black hole, that pit becomes like that. Okay? So if this curvature of space time represents gravity, and that's what it is, it's gravity. This again, this is a bottomless pit of gravity. You don't reach the end of it. Okay? So the force is therefore so strong that again, when you get a little too close to this thing, you're going into that and you're not coming out. Okay? Now, matter in the accretion disk of a black hole, does it have a way of getting out? Yes. To save, like say time, I won't go into details with that. That's what we call Hawking radiation. It's also related to this thing, related things called the Penrose process. But I won't get into that because that's kind of like outside like our class scope, so to speak. Okay. And also, again, I'm not. I say again, as being a non-black hole theorist, I will actually say that that's why I put those videos with Neil deGrasse Tyson and people who are like black hole theorists to get to get clarification on those particular type of questions. Okay, but essentially that's what happens with the black hole. Okay, at the singularity point, singularity, it becomes a bottomless pit of gravity. Okay? So everybody again, keep these going. I'm not saying so now. I make my questions a little bit. My responses a little bit shorter because a lot of these questions are basically are overlapping. Okay. Will the universe keep expanding and will eventually collapse? Say again, your guess honestly is as good as mine because what happens is everyone we just don't know yet. Okay. So what happens is everybody dark energy. I mentioned dark energy before. Dark energy makes up the majority of the universe as far as we know, or at least according to like a lot of models. So what happens, everyone, is that these observations we made suggest that expansion will continue because of dark energy. However, there are two scenarios. One's called the big freeze, the other one's called the big crunch, where in those particular scenarios, the expansion universe does reach to a certain point, and then what happens is with a big crunch in the way, what happens is it'll stop, they'll come back. That stuff start it'll stop expanding. The matter will start falling back in, and eventually the universe will collapse back down into what they call this, and that's what they call the big crunch. With the big freeze, I think that's what if I remember that one correctly, and I don't remember that. I'm not familiar with the big freeze. I just know about it. But what happens with the big freeze, if I remember correctly, is that that's where it actually expands out and like the universe gets really cold and it's essentially that's what happens if the universe gets really cold but you might ask, okay, which one is going to be big freeze or big crunch? That depends on what's the actual geometry and nature of the universe itself. Okay, so that again, that's the best answer I can give. And I could dig into that further, but I didn't want to dig in too far because I didn't want this video to be so long. Okay, I'm already like about an hour in, so close to an hour. So I try to um, keep it to that. My answer to this one to that, and we still got a lot of these to go. Okay, so let's get easy to be. This might end up being about a whole almost like 2 hours. What I'm saying again. So just fair warning about that. So why do stars look like they twinkle? And I know, and the person who asked this question attended one of the stargazer party we already had. So why the stars appear to be twinkling, everybody, is because of the turbulence of the atmosphere. Okay, so if you see this, let me put this flashlight up. Okay, y'all see that light there? So this is my flashlight for my phone. And what I'm gonna do, everybody, I'm gonna shine it through this bowl that's full of like soapy water. So everybody, what happens is if I shine a light through the bowl, you notice how the light wavers around a lot? That's because I'm shaking the bowl. Okay. So again, the reason why the light is wavering so much is because the light is being refracted by the water in the bowl. And if I shake it a lot, you get a lot more of that the light being shimmering around. Okay. So again, that shimmering of the light, everybody, through that bowl, that's kind of like starlight does, or that's what starlight does as it passes through our very turbulent atmosphere. What happens is the gases and aerosols that's in our atmosphere, they're so turbulent as they move around, they slosh around, or as they circle around, or like do all kinds of things. But what happens is everybody, because of that turbulent, saying again, airflow or flow of aerosols. What I mean by aerosols, everyone, I mean things like smoke and dust and stuff like that. But what happens is like light it's like it's being scattered or being refracted by all of that, and so that's why stars appear to be twinkling. It's because again they're being the light is being refracted by the turbulent gases in the atmosphere. Okay, so stars don't actually twinkle. Furthermore, that means that if it had no atmosphere, you're not gonna see stars twinkling. Okay. So next question: what causes a star to have a color such as blue, red, etc.? The short answer: temperature. Okay, temperature is the short answer to that. So what happens, everyone, is that when a star is relatively say kind of hot, it's gonna be red. If it's very hot, it's gonna be going to more like yellow. And by the way, there's no green stars. And the reason why there's no green stars has a lot to do with the quantum, let's say again, the quantum mechanics of the energy levels, saying within the molecules or atoms, at risk, the atoms, and all ions that make up the star. Okay, but like saying, long story short, the reason why say again we get blue, red, or different colors for stars is all about the temperature. The hottest stars are going to be bluer, whereas the stars are not so hot, they're going to be redder. Okay, stars can also be blue or red depending on if they're moving towards or away from the observer. So another reason why a star might appear a certain color is because of what we call a shift due to that star's like saying again position compared to the observer. If the star is moving away from you, it's going to be what we call red shift. So a shift to a lower frequency. Where the star is moving towards you, it's going to be called blue shift. It makes it shift to a higher frequency. Blue is a higher frequency than red. So again, stars are certain colors because of temperature, but also star can also appear to be a certain color, but if it's like say like undergoing some kind of like what we call Doppler shift. By the way, that shift, I mean the red shift and blue shift, that's more a thing with galaxies than stars, to be exact. But still, I need to point that out. But like I say again, really, we talk about the intrinsic actual color of the star. That's related to temperature. Hotter stars are going to be bluer. Okay, this is one of those vague questions. How was time created, and will it ever change again? Okay, time is something that human beings use. Okay, so if like I say so, therefore, like if you're talking about like time itself, like the actual dimension of time, that's a like I say again, that's I'm thinking that we say time change. I think you're talking about time zones here, actually. And actually, let me just answer it from that standpoint. And I'm not talking about like time as a dimension because that's a deep question, and I'm already like gone too deep in certain questions. So if you're talking about time change, you're talking about like daylight savings time and time zones. Those are human change. Those are human things or human made concepts. Read it off to you here. This is what I wrote down. Time zones and daylight savings were human-made concepts for standardizing, let me say it correctly, schedules. Adjustments could occur depending on social social needs or climate condition, climate considerations. Okay, so again, daylight savings time, and Neil deGrasse Tyson is a great view on this. But daylight savings time, everybody, was basically invented such that people can shift their schedule such a way that they can keep time such that like they know when to like go to bed or when to start work that day and things like that. Remember, as everybody saying again, certain times of year the sun goes down sooner, so therefore we mark time such that okay, it's 5 o'clock, but now time is this time of year the sun's going down. Okay, so we move that hour around such that people know when to like say let's say when it's time to like, say leave work and like go get home, eat dinner, say again, have a little like, you know, have a little time that's saying a little leisure time, and then get ready to go to work tomorrow or be ready for the next day, whatever you're doing the next day. All that again, all that time change stuff again was based is human made concepts. Okay, you talking about actual standardized like universal time because we have what we call universal time. Universal time was basically invented such that no matter where you are in the world, you don't have to worry about no time zone or anything like that. And again, time zones occur because the rotation of the planet. Okay, but still, what happens is again, we made universal time such that no matter where you are in the world, people, especially doing astronomy stuff, people can know like what time to actually go out and look at the sky, for example, or if they just want to know, okay, I'm flying on this plane, what time I'm going to arrive to my destination. That's when universal time came about, so people can like not get too confused with time zones. But again, all that stuff is again daylight savings, time zones, human-made concepts. Okay, so be quick about this one. Will there ever be a plant founded and created over time? Yes. There's plants being found and there's plants being created all the time. We found many plants outside the solar system, hundreds, thousands actually at this point. So yes, there's other plants going to be found because there's other plants that have been found, and there are definitely going to be plants created over time because there are new star systems being created as we speak. Okay. Why is there a black hole that's surrounded by a Milky Way galaxy? So essentially, everybody, what happens is it formed when the galaxy was it started forming when the galaxy was young. Okay, and what happens is that probably the center of that galaxy, the reason why it's even there is probably because the gravity. Let's say again, like happens is matter falls inward due to gravity. So probably what happened was when the galaxy formed, that the center of the galaxy got so massive for that particular point in space, it became a black hole. Like again, what happens, everybody? We get so much mass compacted to a small volume. That's how a black hole forms. So you probably got so much mass accreted. Accreted meaning that it collided and stuck together. But what happens, everybody? So much matter accreted at the center of the galaxy, and that got so dense for that particular volume. The gravity of it got so strong that eventually it really became a black hole. And then what happens is, because material was surrounding it still, the matter that was surrounding it, that matter like kept colliding with the black hole, and therefore getting absorbed in, for lack of a better word, and it got bigger. So it kept getting bigger. And so what happens is, the bigger something gets, the more it can eat. That's one guy putting. Now he's talking about planets. That's probably why saying we got Jupiter got to be such a massive planet. It got bigger faster than the Earth did, and therefore it can eat more material. So same thing with the black hole semi galaxy. More likely, what happened was it got big. It was already big. Well, I'll say again, already a black hole, and that black hole just like because it got so strong gravity and so much like but there's so much like matter at the center of the galaxy that the more that matter say it accreted, the bigger the black hole got. So that's it for that one. Again, clarification needed. What are the differences between the many galaxies in space? You're going to have a chapter on this coming up. Next chapter, as a matter of fact, next week. So, why are the differences? What are the differences between the many galaxies? The main thing everybody comes down to is size and shape. Okay, size and shape. We got different types of galaxies. We got what we call spiral galaxies. We have elliptical galaxies, and then we have what we call lenticular galaxies. And so you're going to spend a whole chapter dealing with like what's the difference between these many galaxies. But a lot of times the differences between galaxies come down to size and shape. Okay, probably age too. That matter. How many star clusters are in that galaxy? How many how many supernovae do you have in that galaxy? Those different types of things can make the differences between one galaxy to another. Okay, but again, that's the three main types of galaxies we have: spiral, lenticular, and elliptical. Okay, and also again too, the main difference between those three is size and shape. Definitely shape. Okay, how many the stars within that galaxy? That of course goes back to like those size and shape things. I already talked about this a little bit, so I'm not going to get into more details with this question about if it came down to Earth was no longer suitable for human life. How do we go about forming saying again a plan B? That's what colony on Mars is about. Would it be possible? Yes, but like I say, the thing is, our technology has to improve a lot. We have to we have to really get the ball rolling now. With like saying trying to like build maybe a colony on another planet. Okay, the obstacles you need to overcome it depends on the planet. Now, the most suitable planet was going in our solar system is Venus. I mean, excuse me, Mars. Venus, by comparison, is one of the last places we're ever going to go. Venus is way too um, long gone as far as like being too hot. It's too hot. It's too close to the sun. I mean, it's not suitable at all. Okay, it's covered with lava. It's covered with like volcanic eruptions. So it's just not a super place to go to. Whereas Mars is the most suitable place, let's say again, among the planets. There might be a moon out there that say again might make it too. But the thing is though, everybody, if you go to another world where like you don't have Earth, they don't match Earth in terms of magnetic field, it doesn't match Earth in terms of atmosphere, doesn't match Earth in terms of gravity. The gravity's not maybe like either like too weak or too strong. Those are the problems you're gonna have to overcome. Okay. So again, and also another obstacle is trying to get there. You gotta have a ship to get there too, and more about that later. But I already talked a lot about that with that first question, so I won't go into details of this right now in this video. But again, whoever the student that asked this question, you can ask it again in your comment, and I'll respond to it. Okay? How black holes form? I already talked about that earlier, so just go back to like what I was saying about how they form, like to that example. And what are the dangers of a black hole? Pretty much the gravity of a black hole. If you get a little too close into its event horizon, the event horizon, everybody, is a point of no return. Okay. The reason why we call it the event horizon is because anything that happens within the event horizon, we won't know about. Light or any other light waves will not be able to get out of the event horizon because light can't travel fast enough to get out of a black hole. So what happens is everybody, once you're within the event horizon, we're not gonna know what happens. Okay? And the gravity of the black hole is so strong that it basically will rip apart anything that we know of. Anything. So again, it's just you'll be ripped to shreds. Okay? What happens to a person, let's say an astronaut, and before I move on to the next question. What would happen to an astronaut if they fall feet first into a black hole? Let's say it's our stick man here. He falls into the black hole. So what happens is this person, he falls in feet first. What's going to happen is his body's going to get stretched. Okay, his feet are going to get stretched. So his legs gets longer, his torso gets longer, his neck gets longer, his whole body gets elongated. But the thing is, not only does his body get stretched this way, his body's gonna get compressed the other way. So vertically speaking, he gets stretched. Horizontally speaking, or other sides of his body, he gets compressed. Okay? So this leads to an effect we call spaghettification. So, yeah, spaghettification. So you turn basically a person turns into a stick of spaghetti. Like you see how like you know how stringy spaghetti is. So what happens is that whole person gets like compressed one way and stretched the other way. And of course, naturally, your body can't take that. It's going to be excruciating pain, and you might be bones cracking, flesh bit like muscle, like say muscle tissue, all kinds of tissues are being squeezed and being crushed. So basically, you be stretched and crushed to death at the same time. Yeah, that's the dangers of it. Of let's say falling to it, you probably don't even have to really go get that far into the hole for the gravity to get that strong enough to do that to you. Either. Okay. So yeah, they can be quite dangerous getting into one of them. All right. I often wonder if we will see people living on another planet in my lifetime. Is it possible that occur? That can occur. I have no idea. I don't. In our lifetime, I would say somebody said we've already interacted with aliens or extraterrestrials. I don't think we have. But if we ever see somebody else living on another planet, I'm not sure that'll happen in your lifetime or mine. I'm just not sure about that one. So, is it possible? I would say I can't. I won't say it's not possible. I'll tell you one thing though. They're gonna have to come to us, and you're not gonna get a telescope unless they're sending us a message. We sent a message out actually back in the '70s. We actually sent a message out, transmitted the message from Earth to see if anybody can answer us back. So, and no, we have not heard an answer back. Okay. Somebody said like, no, I think that we have answered back, but the government's trying to suppress that. Well, there's a whole lot of suppressing, considering a lot of people are looking into that. There's going to have to be a whole lot of suppression going on in order to do that. So I don't know. All right. So again, when we see the stars, they appear to be twinkling. Do they have a twinkle effect if we stand in front of them, or if there's a completely different view? Again, the twinkling effect is due to the atmosphere of the planet. Okay. So if you actually right there in let's say if you're right there in space, like do they have a twinkle effect if we were standing directly in front of them? I'm thinking if I'm reading this question correctly, I'm thinking saying that we was actually in the space with them, like where they're located in space. If we were there, and would they appear to be twinkling? The answer is no. Okay. So whether you stand to the side or to the or any other kind of side, it doesn't matter. The twinkling is due to the atmosphere's turbulence. Okay. So again, somebody other people have posted this question already. So like some of you probably just wrote your questions based on what somebody's already asked in the forum. You just rewrote the question. Don't do that next time. Okay. But still, everybody again talk about how far does the universe go? Is it endless? Again, I've already addressed that earlier. So not gonna say that what that the answer to that is. Again, I've already addressed that. The way is there a way for us to learn more about black holes? One have to how close one had to be to wipe out our solar system? A black hole could be just simply at the edge of our solar system, and that would totally mess things up. Okay, so again, one episode of that program, The Universe, one scientist she posed this scenario. If you just happen to put a black hole like maybe on the outskirts of where Pluto is, where Iris is, what happens is it'll pull that. It'll probably if you get close enough to that planet, such that it pulls that planet off course. What happens and just having that mass there probably is going to offset things for the solar system anyway. But if you put that thing a little too close to one planet and drag it off course, what happens is that once that planet gets dragged off course, it's going to eventually cause another planet to get dragged off course, which is going to cause another planet to fall out of its orbit that it should be, and you just have a chain reaction of sorts, or it's not a chain. It's not. Let me not say chain reaction. More like or domino effect. It's more like an avalanche of perturbations, is what we call it in physics. So what happens is, like I say again, like the solar system is well balanced. Okay, it's balanced between, like saying, between the gravitational influences between the sun and the planets and everything else in the solar system. So what happens is, like say, if you throw this that off course just a little bit, it's going to eventually lead to your solar system basically falling apart. Okay, so yeah, you put one right at the outskirts. Yeah, it'll probably mess up the whole solar system eventually. So it won't wipe us out in terms of like it will suck us in. It'll wipe us out in terms of just throwing everything out of whack. Okay, so I think you're probably thinking again, it's like it's going up, sucking up, like saying plants. No, they're not vacuum cleaners. They don't move like that. Okay, but if things get a little too close into them, into their and wait and start getting to their event horizon, yeah, you got a problem. Now, as far as like how do we learn more about black holes? There are several spacecraft missions. Chandra is one mission. That's the Chandra X-ray Observatory. So what happens there, everybody? How do we learn more about black holes? We look for X-rays. We probe, let's say again, space for. What I mean by probe, I'm talking about we send like our telescopes into space and have them observe X-rays and gamma rays. Because what happens is the accretion disk, the disks that form around black holes, they generate a high amount of X-rays. So therefore, we're looking like when we do X-ray astronomy, as we call it, observing like saying outer space for X-rays. We're looking for one of the things we're looking for is activity related to black holes. So long story short, we to learn more about black holes, we again we look for X-rays. That's one of the things we look for. We can also look for things. We can also study more about black holes by using what we call gravitational waves. LIGO. Now this is for X-rays. LIGO, which is an acronym. LIGO is one particular project where they look for black hole activity, but learn more about black holes by using gravitational waves. Now that we determine that gravitational waves indeed exist and they can be detected, we let's say again let's say gravitational waves can help us figure out, let's say again, any kind of activity out there is related to a said black hole. By the way, LIGO's first study or confirmation of gravitational waves came from two neutron stars merging. The neutron stars like spun around each other and they eventually they combined or they merged. That's what they're eventually going to do. But anyway, you have gravitational waves given off by that, and so LIGO was able to detect those. With black holes, on the other hand, any like kind of fluctuations going on with them probably might generate gravitational waves too. Or let's say like some black holes got to orbit each other and want to merge, or they end up merging. The gravitational waves from those events can be detected by LIGO or maybe similar other types of instruments or instruments. Let's say instruments that would be used for that type of research. So, X-rays and gravitational waves. Those two examples of ways we can learn more about black holes. Okay. Does every star get named? No, because every star is not big. It's not basically big enough. My man, big enough. I'm talking about size. Or every star is not bright enough to get named. Okay. And talk about if so. So now every star does not get named. And talk about if so, how do they keep track of them if Earth is constantly rotating and stars burn out? Well, first of all, remember how far away stars are. Stars are many, many light years away from Earth. The closest star to our solar system, I'm talking about not the sun now. That's the closest star we have. That's the closest star to our planet, the sun. But the sun is 8 minutes away, 8 light minutes away, rather. So what happens is we see the sun the way it looked 8 minutes ago. Alpha Centauri is 4 light years away from our planet. I'm 4 light years away from our solar system. So we see Alpha Centauri the way it was 4 years ago. It's 4 light years away. So we see it the way it was 4 years ago. So yes, there's stars in our, out there in our galaxy or stars like beyond our galaxy that we may have observed. That, but most of the stars we observe, of course, will be mostly in the galaxy. But still, those stars out there, what happens there ones that, yeah, they might have already burned out, but the thing is, the light from that event of them burning out or going out hasn't probably gotten here yet. You see some stars that star is like 50 light years away. You see that star the way it was 50 years ago. So therefore, like the reason why is you keep track of them because the light is still coming here. That's how you keep track of them because the light is coming, like saying from them to our planet. And B, and say if they constantly burn out, well, what happens is because they are so far away, the light still hasn't gotten here yet. That star may have burned out, but see, because the light from that event hasn't gotten here yet, we don't know it's burned out yet. We have to wait that amount of time for we actually know that star being gone. So yeah, so that's why I talk about the constant burnout. Again, same thing with the motion. It's because they're so far away. And yes, the Earth is constantly rotating, but still, what happens is those stars are going to last for a long time. Okay, and the light from those events hadn't gotten here is still on their way. So that's why we're able to track them. Because if the star has gone out, the star has gone supernova, or if the star has gone maybe even nova. Nova does not mean the star is dead. That's the star is still alive when it goes nova. Nova and supernova are very different. But still, what happens to everybody is that the light from these events going on with stars, it takes a long time to get here. So therefore, that's why we're able to keep track of them because the light is still on its way. Right? Why is it so important for stars to get named? It's to keep catalogs. It's to keep tabs on things. It's kind of the reason why you still go to the doctor. Okay? Things in the Bible were named so we can understand them. That's part of our way of like studying them and understanding them, right? You got to go to the doctor and say to get checked out because let's make sure your heart is still in order. Well, let's make sure your lungs are still in order. We named all those body parts so we can tell one from the other, first of all. And then second of all, when we go and check on them, we can say again, okay, I'm looking at your heart. Let me see let's see what condition your heart's in. I'm looking at your lungs. Let's see what your lungs condition's in. So catalog, that's really cataloging. Same thing with stars. Well, not the same thing as far as like not checking their health, but I'm saying like as far as like cataloging, you want to have these stars named this catalog so you know what's out there. And then knowing what's out there, that helps you be able to study things, saying in a better way. Okay, so and that's what a lot of times astronomy is about. It's about cataloging what's going on in space so we can understand what's going on out there. Okay, so that's why it's important to know how stars get named. And again, every star doesn't get named. Some stars have a catalog number. Other stars have the brightest stars have names. So the stars that appear to be bright, say again from our vantage point on Earth, those get named. So like Arcturus or Regulus or Rigel, Betelgeuse, those stars are named because they're so bright. The dog star, Sirius, brightest star in the night sky on Earth. Okay, those stars are named because they're so big and bright, and so it makes it. And so also that means that if that star is named, you know what star you're looking at. Just like how saying again, you're looking at the heart because saying I know this thing I'm looking at is what we call the heart. Well, I know this thing I'm looking at right now, we call that the lungs. Okay, so again, that's why it's so important to name these stars. So again, what you're looking at, and also you can do as you do your studies, you can understand what's going on. How's outer space changed over time? If that star did burn out, we don't know. Okay, what star burned out? Well, Betelgeuse not around anymore, man. Betelgeuse done gone supernova. It done blowed up, so it's no longer like a red supergiant star. It's on its way to becoming a black hole now. That's why it's so important to name these things. Are there different types of black holes? Yes. Long story short, the black holes I've been talking about this whole long video is everyone is mainly either stellar mass black holes the mass of a star, or supermassive black holes, which could be like millions to billions of stars in terms of mass. Yes, millions to billions of stars for one supermassive black hole. That's how massive they are. The 1/7 of our galaxy, everybody, is easily millions of billions of times the mass of the sun. But there's also what we call quantum black holes. These are black holes that exist on the subatomic level. And I'm not going into details with them, but yeah, there are different types of black holes. The long, just answer that question. Can a star turn into a planet? No, no, because it can turn into something when a star collapses. It might, I don't know, it might turn into something about the scale size of a planet. What I mean by size, I mean literally the radius of the planet. So in astronomy, we say size, we mean radius. But in terms of like saying again what a planet is, a non-luminous object that happens to be round because of gravity and all that kind of stuff, no. Stars are not turning into planets. Okay? So a star has, in other words, a star has to lose a lot of mass, way too much mass, to become something like a planet. So no, you're not having stars turn into planets. Okay? But good question though. It helps you understand like what stars are about. So what keeps the North Star stuck exactly north and not in any direction? First of all, we have a current North Star. Okay? Polaris is the current North Star. And so what happens to everyone is that Polaris has not always been the North Star. It's the North Star of our many generations that have been living for the last like couple of like millennia. Okay? When the pyramids were built, the North Star was not Polaris. The North Star was actually Thuban. Okay? And so the reason why everybody Thuban was the North Star back then is because that is where the axis tilt of the planet was pointing towards. So let me go back to my globe. Okay? Our planet spins around, things like that, everybody. But the thing about it too, everybody, not only do our planet spins around and it's tilted on its axis, but our planet also wobbles. So this thing spinning and I have this thing wobbling. Okay? Or better yet, let me show it to you using this gyroscope. Our planet Earth is like a giant gyroscope. Okay? So I'm gonna pull the string out of the gyroscope here. This thing spinning. Kind of not spinning fast enough for me to do this. But what happens, everybody, as this thing rotates, it wobbles. Okay? I didn't get spinning fast enough to do that, so I'm gonna try it again. Not now, because in a long video. But everybody, what happens is that as our planet rotates on its axis, it also wobbles too. And so imagine my finger is the tip of my finger. Again, that's the tip of the axis. The axis. This is pointing like saying again north, what we call north on our planet. So currently it's pointing at Polaris, but because this thing wobbles, it's going to eventually point at another star. And then as it continues to wobble, it's going to be pointing at another point in space. Okay? So the reason why it appears to be stuck at that particular position is because of that's where the tilt of the axis is pointing at right now. And the reason why it don't seem like it's pointing in a direction is because unlike a spinning top that can do that in a matter of seconds, our planet does this. It does that wobbling in a matter of thousands of years. Okay, so what happens is that it's pointing towards Polaris right now. It's been that way for maybe a couple hundreds of years to 1,000 years now. But in the next couple of hundreds of years, it's going to be pointing somewhere else. Okay, and over the next couple of hundreds of years to thousands, it's going to be pointing somewhere else. Okay, so it's not actually stuck. It just appears to be stuck over a human lifetime or several human lifetimes. Okay, if you got like say a couple thousand years to live, you're going to see it pointing somewhere else. Okay, and again, this is what happens if you're in a lab. If you take the lab, you can actually see this vividly in the lab. You actually see it simulated in the lab because again, like the whole process, they going like this, Earth doing like that. It takes about roughly 26,000 years to go full circle. So it's not something you're gonna be able to see really appreciably. It's not something you're able to actually see it, directly observe, and put it that way over a human lifetime. Okay. And by the way, it's not the North Star is not actually it's not exactly north. It's a little bit off north, just a little bit. Exactly north is the North Celestial Pole, and the Polaris is slightly off. It's just it's very small. It's very small. Only maybe a few arc seconds, but still, it's not exactly north. Okay, and also the North Star is not going to be the current North Star is not going to be the North Star forever. All right. This is too long of a question for me to get into right now, as far as I get into all the different benefits and drawbacks of space exploration. I'll tell you one of the benefits of it is helping us learn more about space, because what happens is we can't learn everything from telescopes, even spacebound ones, even ones in space. We can't learn everything about space from telescopes. There's a lot of things out there in space that, in order for us to learn about them, we got to actually be there. Okay, we got to be close. That's why we send spacecraft past planets to get an up close look at that planet. The telescope can only give you so much. Okay, if you really want to know what the conditions of that planet is going to be, or it's like, you need to actually fly by that planet, or orbit around that planet, or better yet, land on that planet. And if you get a spacecraft that are saying they allow you to do this, maybe you can actually go to that planet, get a sample, and bring it back. Okay, so the benefits of space exploration is help us learn more about space. Also, everybody, space affects what's on the ground. We can learn more about our oceans by observing it from space, observing Earth from space. So we can learn more about Earth's oceans, for example, by using space-bound space by using spacecraft. And I say that for a reason, because a lot of people think we need to spend more time exploring the oceans than exploring space. But the thing is, we learn about the oceans in one way by using space. So to say like we just like totally like forget about space, let's explore the oceans. No, space helps us explore the oceans. And by the way, exploring the oceans is dangerous, which is one of the drawbacks of space exploration for humans. It's dangerous for humans to explore space. Okay, you're literally in lower gravity. Gravity exists in space. Let me get that out there right now too. Gravity exists in space. What do you think is the force between the Earth and the Sun? It's gravity. There's gravity in space, a lot of it. But the thing is, though, we talk about a small spacecraft in orbit around our planet. That the gravity in that situation compared to the gravity you feel when you're on the ground is much different. And being that lower amount of gravity can have an adverse effect on the human body. Being in space has an adverse effect on the human body because you don't have the protection of Earth's magnetic field or Earth's magnetosphere. So therefore, you're exposed to a lot of radiation that's in space. Okay. I just saw a thing just yesterday. It was actually an episode of, just reminiscing. I watched the episode of Justice League, the anime series that came back. That came on about 20 years ago. And what happens to everyone is that they had one episode. They had this episode. They had these aliens was trying to invade Earth, was invading Earth, but they were trying to block the sun out because they couldn't be in direct sunlight. And the reason why they couldn't be in direct sunlight is because of UV radiation. UV radiation harms them. But as somebody commented on that episode pointed out, that's a plot hole because there's a lot more UV radiation in space than it is going through the atmosphere of our planet. See, our atmosphere blocks a lot of UV radiation. Whereas if you was in you was in outer space, UV radiation, there's a lot more of it could be absorbed by your body if you're in outer space. So again, how those aliens been survive? And how those aliens been survive? You know, saying again, coming to flying through space, and they're able to they can't take UV radiation. They must have some serious shielding on that spacecraft. Furthermore, if you saw more of the episode, it's still a plot hole. Even they have shielded spacecraft. You know, they've been on. They was originally on Mars. They actually took over Mars. But the thing is, Mars has no protection against UV whatsoever. So how they manage to survive on Mars? If they make Mars dark, not according to the flashbacks is a plot hole. Not against. I'm sorry to get into all that, everybody, but long story short, one of again drawbacks of space exploration again is the danger to humans. The other one, of course, is the expense. And by what the dangers to humans, there's a lot of other things I can get into, but for time, I've already been going over like a long period of time now, so I'm not going to get into that right now. But the other drawbacks of space exploration, the main is the expense. It's expensive. Okay, sending rockets up costs millions of dollars, and that's just rockets. Like saying again, not even manned rockets. We're just talking about sending up spacecraft, sending up satellites. That costs a lot of money. That's a lot. Rocketry is still not an exact science. Rockets can still have problems. That's why a lot of times they scrub rocket launches. You know, like they say, like everything is the rocket launch is going up. Everything is nominal. Every time when they say nominal, everybody, when you see a rocket launch, that means that everything is going okay. But sometimes everyone they can have space rockets go up, and next thing you know, they have what they call a RUD, a rapid unplanned disassembly, which basically means the rocket blew up and it got ripped apart, or the rocket, saying getting disintegrated. So rockets can still do that. Okay, so that's one of the drawbacks of exploration. It's still saying the engineering has come a long way, the science has come a long way, but the thing is, it's still not 1% safe as far as or it's 1% accurate. It probably never will be. What is 1% accurate? But we're talking about things made by humans. But still, everybody, what happens is rockets are still not like say again the and we got a lot again. We gotten better. We gotten better. I mean, a lot of rockets are reusable and things like that, or we got reusable ships, or started getting back to using reusable ships. But those things wear down over time. And so therefore, the drawback of any technology, everybody, is going to be the wear and tear on that technology. Okay, so that's one of the drawbacks of space exploration: the expense, the fact that we still got a long ways to go on perfecting anything as far as like launching things in space. We've come a long way. We've done some amazing things. I'm amazed by the things we actually accomplished with it, but we still got a long way. And sending manned missions out into space is going to be very expensive. Very expensive. Sending robots is already expensive, but sending human beings is even more so because robots are, say again, they're not a living things, so they're a lot more expendable. Human beings are not expendable. Okay, so but great question. What do you find in space besides planets and stars? I'll be honest with you. If you've been in this class this many months, you shouldn't be even asking this. But I will answer anyway. There's a lot of things in space other than planets and stars. Comets, asteroids, moons, um, let's say clouds, nebulae, where stars form from. You got to count them too. And there's probably some other things that we haven't found yet. Neutron stars or fast rotating neutron stars, which are called pulsars, black holes. Those things were stars at one point, but they're not stars now. Okay, and then of course white dwarfs, brown dwarfs. A brown dwarf, everybody, is something in between a planet and a star. It's too massive to be a planet, but it's not massive enough to be a star. Those things exist in space as well. And then of course you got things like things that come from space, like it's like meteoroids, and stuff like that. So again, there's a lot of things out there. Okay, why is there a black hole? I'm not. I pretty much answered that already. Why are there black holes? Is really how that should be worded. Why are there black holes? And the reason why is because stars don't live forever, and the most massive ones they collapse down to eventually become what we call black holes. All right. Will there be a spaceship or aircraft that would transport 1 million people at a time to live on another planet? First of all, it's going to be a spacecraft. It's not going to be an aircraft. Second of all, I'm talking about going to another planet because you're going to have to fly through space, you know. But what happens is the technology has to improve a lot, leaps and bounds beyond what we're capable now. Because you know, what I'm saying we've done something. We sent a crew of 5 or 6 people into space. 1 million to another planet. Yeah, some serious engineering science is gonna have to be developed to do that. If we did grow food on another planet, what would taste the same due to climate changes within the planet, or just being on a different planet itself? So again, the way this question is kind of worded kind of strange, but um, if we were to grow food on another planet, basically you're asking, will it taste the same as it does on this planet? The answer is probably not. There's a strong likelihood they will not taste the same. Okay, because again, the flavors and different the flavors that actually had developed over time within the vegetation on our planet, it developed in the system on this planet, with this planet's climate, with this planet's gravity, with this planet's atmosphere. Okay, with the minerals and things like that that make up this planet's soil. Or you know what I'm saying, and I'm saying the actual mass of the actual like um, the plant's actual like saying mass is made of like certain elements. So and those vegetation came from those certain elements, and they're in certain like proportions. So therefore, would they taste the same? The answer is strongly would not taste the same. You grow if you manage to grow like the guy did in the movie The Martian. If you manage to grow potatoes on Mars, they probably won't taste like potatoes on Earth, like the potatoes on Earth. I was, I'm pretty sure those Martian potatoes gonna have a lot more iron in them, so it's gonna probably throw off a lot of the taste. Like that's a potato, like you know, it'd be quite gross to you. Okay, I already answered this question already, so previously, so now we'll get into that now. This is a good one. Why the rings appear some planets but not others? Long story short, gravity. What happens is that the reason why the Jovian planets have rings is because there was probably a lot more debris around those planets when they formed. And so therefore, because of the amount of debris around them, those planets, and because of the large mass of those planets, and therefore the gravity of those planets, they was able to accrete more material to form rings around them. Whereas like Earth didn't quite have enough debris, or as much debris. What debris that Earth did have is probably what ended up in the moon. So Earth ended up with that one, we end up with one moon and no ring. Venus and Mercury don't have moons and also have no rings. Whereas Jupiter has a lot of moons, it has more moons than anybody else. It has little rings. Saturn has almost as many moons as Jupiter, but it's got the most rings of any planet in the solar system. Okay, so two things going on there. Number one is there's some chaos obviously going here because what happens is Saturn ends up with a lot of rings, whereas like Jupiter, Neptune, and Uranus, they have rings, but nowhere near to the same degree as Jupiter does. Saturn does. So whereas Earth could have had a ring, but probably what happened was what debris you had around the Earth that became the moon, and then you have like a few near Earth asteroids, and we do have near Earth asteroids out there. But still, again, the debris, the amount of debris, the amount of accretion going on, or did go on, that was not enough to create a ring. So therefore, we end up with no ring. And Jupiter, even though with all those moons, it got some very wispy ones. Almost like smoke, if you will. The rings around Jupiter. Saturn, on the other hand, look at the rings it's got. It blew everybody else out the water in terms of rings. It's a great question. All right. If we could travel to different galaxies, yeah, good luck. They ever happening. It takes like 100,000 years to go from one side of our galaxy to the other. So, but and that's light moving at light speed. So imagine how fast, how long it's gonna take a human spacecraft at the speeds that we can build them, and how long they could take. You know, could other planets support life like Earth? We have found planets that potentially could be Earth-like, but ultimately to determine whether or not they are Earth-like. And by the way, we don't have to go to another galaxy to find Earth-like planet. We can find Earth-like planets within our own galaxy. So, oh, got my lights. Get the lights back on. Sitting down too long. So everybody again, what happens is if we can travel to different galaxies, could planets support life like Earth? That's possible. So long story short, it's possible. But and we don't have to even travel to other galaxies. We just go to other star systems. Sorry, within our own galaxy. And last question, everyone. All the sources of light, like the sun. I'm guessing that what you meant by this, when you, to whoever wrote the question, are the sources of light like the sun? And the answer is yes. The sun is what we call a G-class star. There are other G-class stars out there. So if you mean sources of light like the sun, if you mean like stars like the sun, the answer is yes. There are stars out there like the sun. There are other G-class stars. Are they exactly alike? Maybe, maybe not. But they're gonna be very similar. They're gonna be within that same class. So yes, they are out there. So that's it for this video, everyone. This is a very long video. So again, watch this in parts, or if you will, I'm gonna tell in the instructions for this voice thread to go to the video, or go to the part of the video where your question shows up and look at that. You don't have to look at the whole thing. If you look at the whole thing, you're a champ, and you're gonna get definitely a lot of points for it. But still, break this video up into like various parts when you see it. So, and that's it for right now. Take care. And again, if you have any questions, make sure you put those questions in your comments.